Ever look at a tiny pill and wonder what's actually inside? We all tend to think about the active ingredient, the drug that's supposed to do all the work. But that, it turns out, is only a tiny, tiny part of the story. Today, we're going to pull back the curtain on the hidden world packed into every single pill. So, just for a second, think about the last time you took a pill or a tablet. What do you picture it being made of? If you're like most of us, you probably imagine it's pretty much 100% the drug itself. But what if I told you that's not even close? The reality is actually kind of wild. In a typical pill, the active drug, the part that gives you the medical benefit, is often just a tiny sliver. The vast majority, we're talking 90% or even more, is made up of stuff called inactive ingredients. Here's a good way to think about it. It's like a Hollywood movie. The drug or the active pharmaceutical ingredient, that's your star of the show. But the star can't do anything without a massive support crew. These other ingredients, the excipients, do everything else. They hold the pill together, they help it dissolve at the right time, they're crucial. But here's the kicker. What happens when the star and their support crew just don't get along? And that, right there, is where our story really begins. Because even though we call them inactive, these ingredients are anything but. They are chemically active, and sometimes, well, they can react with the main drug in ways you really, really don't want. There's a scientific name for this problem: incompatibility. It's a fancy word, but what it means is simple. It's bad chemistry. It's any unwanted reaction that can mess with the final product. And let me be clear, this isn't just a small hiccup. It can seriously impact whether a drug is safe or if it even works at all. I mean, the stakes are incredibly high. When you have good chemistry, everything works as it should. You get a medicine that's stable, effective, and safe. But when you have bad chemistry, the drug can literally break down, become totally ineffective, or worse, form new chemicals that could be harmful. So how can you tell when this bad chemical romance is happening? Well, scientists are like detectives, and they're always on the lookout for clues. Sometimes the signs are obvious, like a pill changing color or getting all clumpy and weird. But other times the problem is invisible, like the drug slowly losing its power or new, unwanted chemicals forming behind the scenes. So to stop this from ever happening, drug companies put every potential recipe through a whole series of intense tests. You can think of it like a scientific matchmaking service, trying to find that perfect, stable partnership between the drug and all its supporting ingredients. And the whole goal of these drug excipient compatibility studies, or DECS, is to be one step ahead. It's all about catching these potential problems in the lab, long before a single pill is ever made for you or me. It's all about prevention. So how's it done? Well, one of the main ways is what's called a solid-state test. First, scientists mix the drug with just one excipient at a time. Then they put that mix through what I like to call a gauntlet of stress. They crank up the heat, pump up the humidity, basically simulating years of shelf life in just a few weeks. They watch for any physical changes, and then they bring in the high-tech tools for deep chemical analysis. And that chemical analysis part, that is where things get really cool. These scientists have a whole detective kit full of amazing gadgets to spot even the tiniest, most subtle reaction. One of their most powerful tools is a machine with a mouthful of a name, differential scanning calorimetry, or DSC for short. What it does, essentially, is use heat in a very, very precise way to see how the drug and the excipient behave when they're mixed together. It's like a fast-forward button, letting them see chemical reactions that might normally take months or years to show up. And the results from a DSC can be incredibly clear. For instance, in one study, scientists tested an antibiotic called afloxacin with lactose, a common filler. The machine showed that the drug's unique chemical signature, its melting peak, completely vanished. That is a massive red flag. It's clear evidence of a reaction, meaning this combination is absolutely incompatible, a definite no-go. But then they swap out the lactose for something else, like starch, and run the test again. This time, a totally different story. The drug's signature peak stays strong and stable. There's no reaction. Ding, 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 we have a winner. This is a compatible match, and this combination gets a green light to move on. Now, DSC isn't the only tool in the kit. Scientists often double-check their work using another technique called thin-layer chromatography. The best way to picture this is like chemical fingerprinting. If a bad reaction creates a brand new substance, it shows up as a new spot on their test plate. It's basically a smoking gun, conclusive proof of incompatibility. Okay, so after all of this mixing and stressing and analyzing with fancy machines, what's the final payoff? The payoff is the safe, stable, and effective medicine that eventually makes its way into your medicine cabinet. And this isn't just some abstract scientific exercise. It matters to you, because this is exactly why your medicine doesn't go bad on the shelf. It's why you can trust that you're getting the right dose every single time. This process is so fundamental to safety that government agencies, like the FDA here in the States, actually require all this data before they'll even think about approving a new drug for sale. And get this, sometimes the science is so smart, it's not just about avoiding bad pairings, it's about creating clever teams. For example, in some injections, the life-saving drug epinephrine can actually be damaged by an antioxidant that's supposed to be protecting it. So what do chemists do? They add another ingredient, sodium borate, that acts like a tiny bodyguard, forming a protective shield around the epinephrine to keep it safe. How cool is that? But chemistry can be sneaky. The process isn't always simple. Take aspirin, for instance. When it's mixed with a common excipient called MCC, all the short-term stress tests look perfectly fine. But over a long time, the MCC can slowly pull moisture from the air, which then causes the aspirin to break down. It's a classic cautionary tale, and that's exactly why scientists have to be so thorough and use lots of different testing methods. In the end, it all boils down to this really powerful idea, summed up perfectly by the researchers themselves. By doing these compatibility studies, they can see potential problems coming from a mile away and design a formula that avoids them entirely. No surprises. So the next time you hold a simple pill in your hand, remember that it's not so simple at all. It's packed with an incredible amount of hidden science and a whole support crew of so-called inactive ingredients that are working tirelessly behind the scenes to keep you safe. It really makes you wonder, doesn't it? What other hidden science is out there, quietly protecting us every single day?